Hi, this is Alex's World of Math, and today we're gonna go through how to solve non-homogeneous recurrences using the characteristic root method. So here's a copy of the steps that you can use to solve it. Um, Particularly, we're gonna use this table to find good hypothesis for particular solutions based on the f of n part, which makes the recurrence non-homogeneous. So first, what you do is you find the homogeneous solution, which is the part without the f of n. So the part that can be expressed as C1 an minus 1 plus C2 an minus 2 plus blah 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 plus ck an minus k. And so you would solve the linear recurrence only using that part, and then that would be the homogeneous solution. And then next, you would have to find the particular solution, which is based on the non-homogeneous part, the f of x. And so you use several hypotheses, and after that, you would try to find like A0, A1, and then after that, you would combine both of them to find the final solution. And you'll probably have like still some variables left from step one that you can use initial conditions to solve for. And know that like step one, you can't use the initial condition yet because that's not the entire solution. Like if you were given say you're um given some initial condition for the entire recurrence, if you use it for the homogeneous part, you're acting like you would be basically saying the homogeneous solution recurrence relation is the entire relation that you're solving for. All right, so you'll see an example of how that works in a second. So basically, just understand that you have to leave all variables alone in step one. Okay, so all right, so get that out of the way. Um, Here's our table we're gonna use. Um, and so our first example that we're gonna explore is a is equal to an minus 1 plus 3, where a1 is equal to 1. All right, so let's identify which part is homogeneous and which one is non-homogeneous, like which parts of this recurrence is homogeneous or non-homogeneous. So obviously, all the terms with an minus k, that can be expressed as something times an minus k, some constant times that is the non-homogeneous, is the homogeneous part. And in this case, you can the an minus 1 is that because you can express that as 1 times an minus 1, where 1 is a constant. And so that's the homogeneous part. We just mentioned that. And we can denote this as an a and h. Sometimes you can use parentheses. Um, And the 3, obviously, you can't express that as any an minus k term. So it's going to be the particular solution uh, denoted by uh, particular solution a and p. Okay, so our step one is to solve the homogeneous solution. So our homogeneous solution is this uh, it's going to be this an minus 1. So we have an is equal to an minus 1. And to solve this linear homogeneous recurrence, all we have to do is use that lambda hypothesis, right? We hypothesize that an is equal to has the form lambda to the power n, and so we substitute lambda to the power n for both to see if it works. We have lambda to the power n equals to lambda to the power n minus 1. Move everything to one side equals 0. We have this. And so we can factor out lambda to the power of n minus 1. From that, we get lambda to the power of 1. Because you can check this, lambda n minus 1 times n lambda to the power of 1 is equal to lambda to the power of n, which gives us the first term, minus 1, obviously, because there's a 0. So this is a general solution. This is the characteristic polynomial. That gives us the characteristic root of lambda is equal to 1. And that also means that lambda to the power of n is equal to 1 power of n. All right, so we have we have uh we have a n minus 1. I'm sorry, a n is equal to 1 to the power of n times a, for a is a constant. Well, actually, let's use a different variable because we're gonna use the a's for the particular solution. All right, so we're gonna have this times let's say b. So we have a n equals to 1 to the power of n times b, which is also equal to just b, but yeah, we can leave that for now. And this is the part where I say leave the b alone because we can't solve for b for now because an this an, quote unquote an in this case, is actually the homogeneous part. So this is not the entire recurrence relation that we had before, which had the condition a1 equals 1. We don't have any conditions for our homogeneous part. So we have to leave this by itself and solve this after we combine everything together. So yeah, so let me move this part here. And let me erase our work. All right, so we've solved for the homogeneous part. Now the particular solution. We have that um we have that uh, uh yeah. So for the particular solution, 3 is not directly equal to the particular solution. We're just saying that the particular solution is based off of that. So basically, a better way to write this is, I mean, yeah, it's part of like it's a region, it's a place that makes it non-homogeneous, right? But this would basically be our f of n, our f of n. And basically, so it's equal to f of n, right? So let's look at our chart. So f of n, so we see if we have a constant, our particular solution would be in the form of a constant. That's one of the hypotheses that we are led to. So let's use the constant hypothesis. All right. So if we hypothesize that the particular solution would be in the form of a constant, then we're basically saying A and P is equal to A. All right. Um, so that's our hypothesis. Similar to how we set the hypothesis for the homogeneous part, where A and H is equal to lambda to the power of n. And in this case, we do the same thing. We plug in every an that we see with this hypothesis, and so an gets substituted with a is equal to an minus 1 is also a plus 3. But do you see how like this does not work, right? Um, because 0 is not equal to 3. If you cancel these out, 0 is not equal to 3. Because in the why do you plug in A for the entire equation? It's because that's the step for the particular solution. You find a hypothesis and then you plug it back into the main equation, unlike the homogeneous part. Because this entire equation is quote unquote non-homogeneous, and so the particular solution would account for all. And so what that means is that we cannot use this for as our hypothesis um, for the particular solution. So we must pick a different kind of hypothesis. So the next best thing would be to use the linear one. So we have a0 plus a1 n, and if we substitute that in for an and an minus 1, um, we have that a0 plus a1 n is equal to a0 plus a1 times an plus n minus 1 plus 3. Okay, so now we have this equation. The a0 cancels out. We have a1 n equals to a1 n minus a1 plus 3. And these cancel out too, so we have a1 is equal to 3. All right, so a1 is equal to 3. A0 we don't have a value for because whatever value we plug in for A0, it all works. So that means that A0 does not matter to us. Okay. So in a particular solution hypothesis, you don't like you want to have parts that change and are characteristic to the main solution. That's why it's called a particular solution. It's a particular solution. It's not like a general solution. And if we included the A0, it's going to be a general solution because we don't know because any value for A0 works, right? Uh, like if you had like this is the same thing as saying like mx plus b. Say you had like uh y equals to 3x plus b. And you're leaving this b here. That means this form is a general form, right? Because it accounts for any value of b. Same thing here. We're saying any value of a0 would be our general solution, but we literally want the particular solution, right? So we don't include that. Um, and so our hypothesis for the parts that do affect the recurrence would be a1n, which we evaluated to be 3n. And so now we have our particular hypothesis, solution hypothesis, and we solved for a of n, a of 1. And so now we are able to go to step 3, right? Because we have both the particular and the we have both the particular and the um the homogeneous solutions, right? For a of n. So this is 3 of n. 3n. All right, so now moving on to step 3, we have step 3 where we have the main uh, the main recurrence, function a of n is equal to a of n of homogeneous plus a of n the solution for particular, which is also equal to 1 to the power of n times b plus 3n. And now we can just use the initial condition a1 is equal to 1. All right, so a1 is equal to 1. So we plug in n equals to 1, we get a1 is equal to 1 to the power of n times b. In this case, n would be equal to 1 plus 3 times 1. So we have and this is equal to 1 because a1 is equal to 1. So we have b plus 3 is equal to 1. We have b is equal to -2. And so now we have our final solution. A of n is equal to 1 to the power of n times -2 plus 3n. And we know 1 to the power of anything is equal to 1, right? So this is also equal to -2 plus 3n. And that makes sense, right? Because a recurrence adding 3 every single time would basically be like expressing an arithmetic sequence, right? And an arithmetic sequence adds 3 every single time, right? For every recurrence, it's defined as when you have uh you know a1 is equal to, yeah, like this recurrence is the same as the arithmetic sequence where a1 is equal to 1 for um fn is equal to 1, and we have that a of n minus 1 plus 3 if n is greater than 1. And so sorry, you just write 1. All right, so this is the recursive definition of the arithmetic sequence, and to express this arithmetic sequence as an explicit formula form, we have found that a of n equal to this. So yeah, and if you want to just test out, you start with say a2, right? A2 is when n is equal to 2, so we have plus 3 times 2 is equal to 4 because 6 minus 8 is 4. And if you use the recursive definition, you have that right here. Use this one, or even just the recursive definition. You have that a of 2 is equal to a of 2 minus 1, which is equal to 1 plus 3. And then we know a1 is equal to 1, so a1 plus 3 is equal to 4, and it is indeed 4, right? So our solution was correct. All right, let's try another problem. Um, let's try like a little little more complex problem that doesn't just have one, you know, just one simple term. So we have, let's try a of n is equal to 3an minus 1 plus 2n, where a1 is equal to 3. So in this case, let's identify our homogeneous part. Our homogeneous part is this, right? As a n h, and this part is our f of x, which makes it non-homogeneous in its entire sequence. All right, so I meant recurrence. And so we can first go to solving the homogeneous part, and so we have an is equal to 3an minus 1. How do we solve this recurrence? We use the lambda hypothesis again, and so we have lambda to the power of n minus 3 lambda to the power of n minus 1 if we move everything to one side, because we have like an minus 3an minus 1 is equal to 0. And we just substitute every an with the lambda to the power of n, because if we have an minus 1, we have lambda to the power of n minus 1. And so now we can again factor out the n minus 1, lambda to the power of n minus 1, and we get lambda to the power of 1 minus 3 equal to 0. This is the general solution, and this is the characteristic polynomial. And so we use the characteristic polynomial to get the characteristic roots, and we obviously find that lambda is equal to 3, right? Um, and so that also means that lambda to the power of n is equal to 3 to the power of n, and we have the general form a of n is equal to h is equal to some 3 to the power of n times let's use b again as b. Okay. And so that's our homogeneous solution, which we will leave it in this form. We'll leave the b by itself for now. All right. And now we solve for the particular solution. So we see that 2n is in the form of this one, right? So let's use the linear hypothesis. All right. And so using a linear hypothesis, we can denote the particular solution in this form where this is equal to a0 plus a1